Welcome to this problem walkthrough. Today, we'll solve LeetCode problem number 1485, titled Clone Binary Tree with Random Pointer. In this problem, we'll explore how to create a deep copy of a binary tree where each node has left, right, and random pointers. Let's dive in and break it down step by step. In this problem, you are given a binary tree where each node has three attributes. First, there is a pointer to the left child and another pointer to the right child, just like in a standard binary tree. However, there's also a third pointer, called the random pointer, which can point to any node in the tree, or it could be null. Your task is to clone this binary tree. The clone tree needs to have the exact same structure as the original tree, including the same node values. Additionally, the random pointers in the clone tree must point to the corresponding clone nodes. For example, if a random pointer in the original tree points to a specific node, the random pointer in the clone tree must point to the clone of that specific node. You will be given the root of the original binary tree as input, and your function must return the root of the clone tree. The input format specifies that the root of the binary tree will be provided, with each node containing three attributes: the value of the node, a pointer to the left child, and a pointer to the right child. Additionally, each node has a random pointer, which can point to any other node in the tree, or it can be null. The output of your function should be the root of the cloned binary tree. This clone tree must replicate the structure of the original tree, meaning all nodes and their left and right child relationships should remain the same. Furthermore, the random pointers in the clone tree must mimic the behavior of the random pointers in the original tree, pointing to the corresponding clone nodes. To help clarify this problem, let's look at an example. Suppose the input is a binary tree where the root node has a value of 1, with two children, node 2 on the left, and node 3 on the right. Node 2 has a right child, node 4, while node 3 has a right child, node 5. Random pointers are also included. For instance, the random pointer of node 1 points to node 3, node 2's random pointer points back to node 1, and so on. The goal is to produce a clone tree that has the exact same structure and values, with the random pointers in the clone tree pointing to the corresponding clone nodes. The output for this example would be a cloned binary tree with the same structure and node values. This means the clone tree will also have a root node with a value of 1, node 2 as its left child, node 3 as its right child, and so on, matching the original tree exactly. The random pointers in the clone tree will also follow the same pattern, but instead of pointing to the nodes in the original tree, they will point to the corresponding nodes in the clone tree. For instance, if the random pointer of node 1 in the original tree points to node 3, the random pointer of the clone node 1 will point to the clone node 3. Now, let's consider a second example. In this case, the input binary tree has a root node with the value 7, and two children, node 13 on the left and node 11 on the right. The random pointers in this tree form a specific pattern. The random pointer of node 7 points to node 11, while the random pointer of node 13 points to node 7. Similarly, the random pointer of node 11 points back to node 13. The output for this example would be a cloned binary tree with the exact same structure and values, where the random pointers follow the same relationships as in the original tree, but they point to the corresponding clone nodes instead. Lastly, let's review the constraints and edge cases for this problem. The tree can have up to 1,000 nodes, and each node's value is unique and lies within the range of -10,000 to 10,000. The random pointers can point to any node in the tree, including null. For edge cases, if the input tree is empty, meaning the root is null, the output should also be null. Similarly, if a random pointer in the original tree points to null, the corresponding random pointer in the clone tree should also point to null. Additionally, if multiple random pointers in the original tree point to the same node, the corresponding random pointers in the clone tree should all point to the clone of that node. To solve the problem of cloning a binary tree with random pointers, our objective is to create a deep copy of the tree, ensuring that each node's left, right, and random pointers are correctly set. The random pointer adds complexity, as it can point to any node within the tree or be null. One approach we considered is the brute force method. The intuition here is to break the problem into two clear steps. First, traverse the tree to clone its structure, focusing only on the left and right pointers while maintaining a mapping between the original nodes and their clone counterparts. Second, perform a second traversal to assign the random pointers for the clone nodes by leveraging this mapping. While this method is straightforward, it requires additional space for the hash map and involves traversing the tree twice. This results in a time complexity of O, n, and a space complexity of O, n, making it a simple but memory-intensive solution. An alternative to the brute force method is an optimized approach that reduces space complexity by temporarily modifying the original tree during the cloning process. The key idea is to interweave cloned nodes directly into the original structure. For example, if we have a node, we insert its clone as its left child. By doing this, we can set the random pointers for the cloned nodes by directly accessing the random pointers of their corresponding original nodes, all within a single pass. Once the cloning is complete, we perform a second traversal to separate the cloned nodes and restore the original tree to its initial state. This method has the same time complexity of O, n, but reduces space complexity to O, h, where h is the height of the tree, as it avoids the need for an explicit hash map. However, it does involve temporarily altering the tree structure, which requires careful implementation to ensure it is restored correctly. The optimized approach was selected as our solution because it offers superior space efficiency without compromising the time complexity. By interweaving the cloned nodes within the original tree, we eliminate the need for an additional hash map, which significantly reduces memory usage. This approach is both elegant and practical, as the temporary modification of the tree is reversible and does not affect the correctness of the solution. A key realization that guided this choice was understanding that the tree itself can serve as a temporary data structure for storing mappings, enabling us to avoid additional space overhead. Compared to the brute force method, this strategy is more efficient and scalable. While it requires careful handling to restore the original tree structure, the trade-offs are well worth the benefits, making this approach the clear winner for this problem. In conclusion, the optimized approach strikes the perfect balance between time and space complexity, making it an ideal solution for this problem. It is both efficient and scalable, adhering to the constraints while maintaining clarity and elegance in its implementation. By leveraging the tree itself to store temporary mappings, we minimize memory usage and ensure the method is practical even for large input sizes. This strategy not only solves the problem effectively but also demonstrates how thoughtful algorithm design can lead to significant performance improvements. In this problem, you're tasked with creating a deep copy of a binary tree where each node has 3 pointers: left, right, and random. The random pointer is unique because it can point to any node in the tree, including itself, or it can be null. The goal is to replicate not only the tree structure and values but also the exact randomized connections of the original tree. To solve this, we use a 2-pass strategy. The first pass focuses on cloning the tree structure without worrying about the random pointers, while the second pass handles the random pointers using a hash map. The hash map, which maps original nodes to their corresponding clones, plays a pivotal role in ensuring that we can efficiently resolve these connections. We begin by validating the input. If the original tree is null, we simply return null. After that, we initialize 2 key data structures, a hash map to store the mapping between original nodes and their clone counterparts, and a queue to facilitate a level-order traversal. This traversal allows us to clone the left and right children of each node while building the tree structure in the first pass. As the level-order traversal progresses, we connect the cloned nodes' left and right pointers to their respective clone children. If a node has children, we also push the original children into the queue for further processing. Once the entire tree structure is cloned, we move on to the second pass, where we handle the random pointers. Here, we iterate over the hash map. For each original node, we retrieve its random pointer and use the hash map to find the corresponding clone node for the random target. This clone node is then assigned to the random pointer of the clone node. If an original node's random pointer is null, we simply set the cloned node's random pointer to null. Finally, we return the cloned root node from the hash map, which represents the deep copy of the binary tree. The solution hinges on a few key insights. First, the hash map is critical for maintaining a one-to-one mapping between original nodes and their clones. This allows us to resolve random pointers in constant time, which is essential given the potential complexity of these connections. Second, the 2-pass approach ensures that we separate concerns effectively. In the first pass, we focus solely on cloning the tree structure, ensuring that all nodes are created and added to the hash map. This guarantees that when we reach the second pass, we can resolve all random pointers without encountering any missing nodes. Third, it's important to handle edge cases carefully. For example, the input tree could be null, certain nodes might have null random pointers, or a node's random pointer might point back to itself, creating a cycle. These scenarios must be addressed to ensure the solution is robust. The algorithm relies on two primary data structures. First, the hash map, which maps each original node to its corresponding clone. This allows us to perform constant time lookups when resolving random pointers. Second, the queue is used for the level order traversal during the first pass, enabling us to clone the tree structure iteratively. In terms of complexity, the time complexity is O(n), where n is the number of nodes in the tree. This is because each node is visited once during the first pass to clone the structure and once during the second pass to copy the random pointers. Hash map operations, such as insertions and lookups, are O(1) per node. The space complexity is also O(n), as the hash map stores n mappings, and the queue can hold up to n nodes in the worst-case scenario, such as in a complete binary tree. These efficiencies make the solution both scalable and optimal for this problem. Here, we start by defining the structure of our binary tree node using the node class. Each node contains a value, pointers to its left and right children, and an additional random pointer, which can point to any node in the tree or be null. In the solution class, we define the main function, copyRandomBinaryTree, which takes the root of the original tree as input. The first step is to handle the edge case where the root is null, in which case we simply return none. Next, we create a dictionary called node_map to keep track of the mapping between original nodes and their corresponding cloned nodes. This ensures that each node is cloned only once. We also define a helper function, get_cloned_node, which takes a node as input and returns its corresponding clone node. If the node hasn't been cloned yet, we create a new node instance with the same value as the original and store it in the node_map. This function ensures that we can efficiently retrieve or create clones of nodes as needed. Now, we implement the DFS function to traverse the tree and copy its structure. For each node, we first use the get_clone_node helper to clone the current node. Then, we recursively call the DFS function on the left and right children of the original node, assigning the cloned left and right subtrees to the corresponding pointers of the clone node. Additionally, we handle the random pointer by cloning the node it points to using the same helper function. Finally, the cloned node is returned. To begin the cloning process, we call the DFS function with the root of the original tree, and the function recursively builds the entire clone tree, including all left, right, and random pointers. The result is a deep copy of the binary tree, which is returned as the output of the copyRandomBinaryTree function. Here, we're starting with the class definition and setting up the structure for our solution. We have a class node that represents each node in the binary tree. Each node has a value val, pointers to its left and right children, and a random pointer, which can point to any node in the tree or be null. Next, in the solution class, we define our main method copyRandomBinaryTree, which takes the root of the original binary tree as input. To handle edge cases, the first thing we do is check if the root is null. If it is, we simply return null since there's nothing to clone. Then, we set up a hash map called nodeMap. This map will help us store original nodes as keys and their corresponding clone nodes as values. This will be crucial for efficiently handling the random pointers later in the process. Finally, we define a helper method, which we will complete shortly, to get the cloned version of any node. The helper method getCloneNode is designed to ensure that each node from the original tree has a corresponding clone node. If the input node is null, it simply returns null. If the node isn't already in our node map, we create a new clone node with the same value as the original and store it in the map. This ensures that each node is cloned only once, and we can retrieve the clone node efficiently when needed. Next, we define a recursive DFS method that will traverse the original tree and construct the clone tree. If the input node is null, the method returns null. Otherwise, it retrieves the cloned version of the current node using getCloneNode. For the left and right children, we recursively call DFS and set the clone node's left and right pointers. For the random pointer, we use getCloneNode to retrieve or create the clone of the node that the random pointer references. This way, the clone tree mirrors the structure and random pointer connections of the original tree. Finally, we invoke the DFS method starting from the root of the original tree. This kicks off the recursive process of cloning the entire tree node by node. The DFS method handles cloning the left and right children, as well as the random pointers, ensuring that the clone tree matches the original tree in both structure and random pointer connections. Once the traversal completes, the root of the clone tree is returned as the result of the copy-random binary tree method. With this implementation, we efficiently clone the binary tree while preserving all the random pointer relationships, thanks to the hash map that maps original nodes to their clones. This ensures that the solution works in n time, where n is the number of nodes in the tree, as each node is visited and processed exactly once. In this example, we have a simple binary tree with 3 nodes, 1 as the root, and 2 and 3 as its left and right children, respectively. None of the nodes have random pointers, as all of them are set to null. To clone this tree, we start by initializing an empty node_map that will store mappings between the original nodes and their clones. We then perform a depth-first search, starting with the root node, which has a value of 1. Since node 1 is not yet in node_map, we create its clone, node 1, and add the mapping to the map. Next, we proceed to explore the left child, node 2. For node 2, we repeat the process, we create a clone, add it to the map, and since both of its children are null, we return the clone node 2. Similarly, we perform DFS for node 3, creating its clone and adding it to the map. After processing both children of node 1, we attach the clone node 2 and node 3 as the left and right children of the clone node 1, completing the cloning process for this tree. The final output tree is identical in structure to the input tree, with nodes 1, 2, and 3 cloned and connected appropriately. Now, let's explore a more complex example where the binary tree also contains random pointers. The tree structure remains similar, but with additional random pointers. Node 1 points to node 3, node 2 points to node 4, and node 3 points to node 5. We begin by initializing the node_map and performing DFS starting from the root node, which is node 1. The cloning process is similar to the previous example, but this time we also map the random pointers during the traversal. For node 1, we create its clone and recursively process its left child, node 2. For node 2, after cloning it, we move to its right child, node 4. Node 4 is cloned, its children are processed, both null, and we map the random pointer of node 2 to the cloned node 4. Returning to node 3, we create its clone, process its right child, node 5, and map the random pointer of node 3 to the cloned node 5. Finally, for node 1, we map its random pointer to the cloned node 3 and attach all the cloned children. The output tree retains the original structure, with correct random pointer mappings. Node 1 points to node 3, node 2 to node 4, and node 3 to node 5. To break this down further, the DFS traversal ensures that every node is cloned and its structure is replicated correctly. Starting from node 1, we recursively clone each child node and map their random pointers. For node 2, after creating its clone, we process its left and right children. The left child is null, so we move to the right child, node 4. Node 4 is cloned, and since it has no further children, the cloned node 4 is returned. At this point, we set the random pointer of the cloned node 2 to the newly cloned node 4. Similarly, for node 3, we clone it and process its right child, node 5. After cloning node 5 and completing its traversal, we map the random pointer of the cloned node 3 to the cloned node 5. This process ensures that all random pointers from the original tree are correctly replicated in the cloned tree. With the cloned children and random pointers in place, we return to node 1 to finalize its structure. Once node 1's children have been cloned and processed, we map its random pointer to the cloned node 3. At this stage, both left and right subtrees of the root node have been fully replicated, and all random pointers have been correctly assigned. The cloned children, node 2 and node 3, are attached to the root clone, completing the cloning of the entire tree. The final output is an identical tree structure with random pointers preserved. Node 1's random pointer points to node 3, node 2's random pointer points to node 4, and node 3's random pointer points to node 5. This demonstrates that our algorithm effectively handles both the structural duplication and the additional complexity introduced by random pointers, producing a deep copy of the original binary tree. Finally, let's consider an edge case where the tree consists of a single node, and its random pointer points to itself. Here, we simply clone node 1, and since it has no children, the cloning process is straightforward. The key step is to correctly map the random pointer of the clone node 1 to itself. Once this mapping is established, we return the clone node 1 as the output. The final tree consists of a single node with its random pointer correctly pointing back to itself, demonstrating that the algorithm handles this special case efficiently. To analyze the time complexity of our solution, we start with the depth-first search traversal. The DFS function visits each node exactly once, meaning the traversal is proportional to the total number of nodes in the tree, denoted as n. This gives us a time complexity of O, n, for the traversal. Next, for each node, we use the helper function get_cloned_node to check if the node has already been cloned. This involves a dictionary lookup, which on average takes constant time, or O1. Since this function is called for every node during the DFS, this step also contributes O(n) to the time complexity. Lastly, the random pointer for each node is processed in constant time, just like the left and right child pointers. Again, since there are n nodes, this step adds another O(n). When we combine all these steps, the overall time complexity for the solution is O(n). Now, let's consider the space complexity. One major component is the node_map dictionary, which stores mappings from the original nodes to their cloned counterparts. Since every node in the tree is cloned exactly once, the space required for node_map is proportional to the total number of nodes, or O(n). Another component is the recursive call stack used during the DFS traversal. In the best-case scenario, where the tree is perfectly balanced, the height of the tree is O log n, so the stack space would be O log n. However, in the worst-case scenario, where the tree is completely skewed, the height of the tree is O(n), and the stack space also becomes O(n). Therefore, the total space complexity is dominated by the node_map and the stack usage, leading to an overall space complexity of O(n). This solution is more efficient compared to a naive approach that might construct the tree in multiple passes. For example, a naive method could involve one traversal to clone the structure and additional passes to handle random pointers, resulting in a time complexity of O(k*(n), where k is the number of passes. In contrast, our solution achieves efficiency by processing all pointers left, right, and random within a single DFS traversal. The use of a dictionary ensures that cloning each node is done in constant time, or O(1), which further reduces time complexity compared to approaches that rely on additional lookups or structures. This optimization allows us to achieve O(n) time and O(n) space in a single pass, making the solution both time and space efficient. Finally, let's analyze the best, average, and worst cases. In the best case, where the binary tree is perfectly balanced, the height of the tree is O log n. This results in O(n) time and O(n) space, with minimal call stack usage. For the average case, where the tree has a random structure, the time complexity remains O(n), and the space complexity is primarily determined by the size of the node_map, which is O(n). In the worst case, where the tree is completely skewed like a linked list with all nodes in a single line, the time complexity is still O(n), but the call stack usage increases to O(n), leading to an overall space complexity of O(n). Mathematically, since each node is processed exactly once and each of its pointers is handled in constant time, the work per node is constant. This ensures a total time complexity of O(n). The space complexity is driven by the linear growth of node_map and the call stack height, which together result in O(n) space usage. When working on this problem, there are several common mistakes that can trip you up. First, neglecting the random pointer is a frequent error. Many solutions focus solely on cloning the left and right pointers but fail to account for the random pointer, which can point to any node in the tree or even be null. This oversight leads to an incomplete or incorrect deep copy. Another pitfall is using additional space inefficiently. While using a hash map to store mappings of original nodes to clone nodes works, it introduces O(n) space complexity. This is suboptimal since in-place solutions can achieve O(1) space. Modifying the original tree permanently is another issue. Some approaches embed clone references directly into the original tree, but if the tree isn't restored afterward, it could cause errors in scenarios where the tree is reused. Edge cases, like an empty tree or a tree with just one node, are also often overlooked and can lead to runtime exceptions. Lastly, recursion on very large trees can result in stack overflow errors. Iterative solutions or tail recursive optimizations are better suited to address this problem in such cases. Now, let's consider insights that are especially relevant for interviews. This problem is essentially a variation of deep copy problems, like copying linked lists with random pointers. The random pointer introduces nonlinear references, making the cloning process more complex. It's important to aim for an optimal solution with O(n) time and O(1) space, and one effective strategy involves temporarily modifying the tree by interweaving the original and clone nodes, then restoring the tree afterward. If you opt for a hash map-based approach, make sure to articulate the trade-offs clearly. While it simplifies implementation, it uses extra space. Demonstrating an understanding of both approaches shows adaptability. Additionally, always discuss edge cases during interviews, such as handling empty trees, single-node trees, or trees with deep nesting. Addressing these demonstrates thoroughness in your thought process. There are several related problems that can help you draw connections and deepen your understanding. Problem number 138, copy list with random pointer, is a direct parallel where the random pointers require careful handling, similar to this one. Problem number 105, construct binary tree from pre-order and inner traversal, focuses more on tree reconstruction, but it builds your skills in managing pointers. Problem number 133, clone graph, deals with deep copying in the context of graphs, where arbitrary connections can exist between nodes. Lastly, problem number 897, increasing order search tree, emphasizes modifying and restoring the structure of a binary tree. Exploring these problems can provide you with valuable patterns and techniques that are applicable here. Finally, let's discuss alternative approaches to solving this problem. A hash map-based approach involves traversing the tree twice, first to clone the basic structure and then to update the random pointers. While this is simple to implement, it requires O(n) extra space for the hash map. Another method is the in-place interweaving approach. Here, you temporarily modify the tree by interweaving clone nodes with original ones. This allows you to establish the random pointers without extra space, and you then restore the tree and separate the clone. This approach is optimal in terms of space but can be trickier to implement due to its complexity. Lastly, consider recursive versus iterative solutions. Recursive solutions are intuitive but prone to stack overflow in deeply nested trees. Iterative methods, which use a stack or queue, are more robust but can be harder to write. Choosing the right approach depends on the constraints and requirements of the problem you're solving. Great job! To recap, we solved the problem by using a hash map to efficiently clone the binary tree with random pointers. Remember, mastering pointer manipulation and deep copy techniques is essential for tackling advanced data structure problems. Thanks for watching, and stay tuned for more coding challenges. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!